Okay. So let's talk a little bit about getting distances via this Hubble law, as we call it. All right, so as I said, Hubble's law is not a standard candle method. It uses the red shifts of objects to determine distances rather than intrinsic luminosities. That's because we have to know something about the expansion rate of the universe as a whole to get this method to work. So we'll have to talk a little bit about the universe. But first, I want to talk just a little bit about the true universe. So it wasn't until the 1910s and 1920s that astronomers had enough data to confirm that there was even a universe beyond the Milky Way. I want to make this clear. Before essentially 1924, we didn't know there was a universe outside the Milky Way. We thought the entire universe was the Milky Way. So this modern cosmological idea of our universe is very recent. It's only about 80, well, almost 100 years old, because it started with the first galaxy redshifts, which were taken in the around 1912. So no one really understood the concept of external galaxies, although some people had predicted that these things that they called spiral nebula were probably outside the galaxies. Immanuel Kant called them island universes in his treatise of 1755. But those were kind of speculative things. They didn't have the data to support it until, let's say, the 1920s. So until then, the universe was really just the Milky Way. That was it. So it sounds kind of lame, right? It's almost as bad as the ancients, with the whole universe being the solar system. And we thought the whole universe was the Milky Way until 100 years ago. So again, they found these things that they were calling spiral nebula, which we know today are actually spiral galaxies. And they were detecting redshifts. The first redshift of a spiral nebula was detected in 1912 by a guy named Vestal Melvin Slipher. He was observing at this Lowell Observatory. And that's the same observatory that was built by that guy who found canals on Mars. So he's using a telescope built by that millionaire guy. But he wasn't quite as wacko as the designer of the guy who paid for the observatory. A lot of astronomers thought that those spiral nebula, even with these Doppler shifts, again, they were measuring Doppler shifts of these objects. They could measure the spectral lines in these spiral nebula, and they could see hydrogen lines, calcium lines. They could see that they were redshifted, and some were even blue shifted. Okay? The first object that was observed was actually blue shifted. It's actually coming towards us, the Andromeda Nebula. Other people thought they were external objects, and there was a tremendous debate that went on in around 1920 between these two guys, this guy named Shapley and another guy named Curtis, and they were debating, first of all, whether or not these spiral nebula were external to our galaxy, and they were also debating whether or not our own solar system was at the center of the Milky Way. And it wasn't until 1924 that they would realize that, first of all, these were external galaxies, and that we are also not at the center of the Milky Way. As you know, we're on one of these spiral arms about 2/3 of the way out. So it is 1924. Hubble uses the world's biggest telescope, a 100-inch telescope at Mount Wilson, still in operation. And he finds one of these Cepheid variables that Henrietta Leavitt had discovered in the Andromeda Nebula. He found a Cepheid variable in one of these weird things that had a kind of high blue shift, as the case may be in this case. And he found out that this thing definitely had to be outside of the Milky Way. Here he is. I think he's posing for photographers. I don't think he actually sat at the focus and looked at the eyepiece so much of a 100-inch telescope. He usually used gigantic photographic plates. So he proves that the Andromeda Galaxy resides beyond the Milky Way, realizes the Milky Way is not probably the center of the universe, and it's really the first proof until 1924 that there are other galaxies in the universe besides the Milky Way. Okay, as I said, this guy Slipher, here he is. He's probably the best dressed astronomer you're ever going to see. He wearing a really beautiful cravat. I can't afford those kind of clothes for the salaries they pay me. He had been observing redshifts in different spiral nebulae, but they didn't understand them in the very beginning. And they thought maybe they were objects traveling in the Milky Way. But eventually, as I said, Hubble and others started to measure distances to these objects. But the Cepheids, at that time, the technology wasn't so great for the more distant objects that they were finding. They were finding more and more of these galaxies with higher and higher redshifts. A few had blue shifts, but most had redshifts. They were observing more and more. They were finding, for some reason, most of the galaxies he was observing were going away from us. They had high Doppler redshifts. So their spectrums were all shifted towards the red part of the spectrum. So definitely traveling away from us. So since they couldn't use Cepheid variables for some of those fainter ones, Hubble said, well, why don't we just use the brightest stars? That's not an unreasonable thing to assume. It's kind of like main sequence fitting we talked about. I can just assume, well, the brightest star in any galaxy, or the brightest stars in any galaxy, are probably O stars. That's on the leftmost part of the HR diagram. They're super bright. I can get an idea of what those objects' intrinsic luminosities are. He says, why don't I use those? Maybe those will be good enough. So he does. He tries to use those. But around the same time, people were starting to realize that Einstein's theory of general relativity could also tell us something about the universe itself, the life history of our universe, how the universe came about. And this guy, Georges Lemaître, he's a Belgian priest, but he's also a brilliant mathematician and astronomer. He was educated at MIT. He did a master's degree at MIT, and he got his PhD, I think, in Leuven. He worked with Arthur Eddington in Cambridge. Had a very good pedigree. He's a brilliant mathematician. He solves Einstein's general relativity equations in 27, and he realizes that when he solves those equations, he gets a distance redshift relationship. So he says, look, we're seeing all of these galaxies traveling away from us at tremendous speeds, and I think that those galaxies that travel at higher and higher speeds are farther and farther away from us. That's what my solution to Einstein's equations is telling me. He's not the first one to solve these equations. Actually, he's the second. The first guy to do it was a Russian mathematician in 1922, but his solutions were forgotten completely. Even though the guy wrote Einstein with his solutions, Einstein didn't like his solutions. He said, actually, I think your solutions are wrong. The guy writes Einstein back and says, no, you're wrong. My solutions are right. And another guy convinces Einstein that, yes, indeed, the solutions are right, but then the solutions are forgotten by everybody for some reason. But anyway, this guy comes along 5 years later and solves the same equation, but he's an astronomer. He knows much more about astronomy data. This guy was really a mathematician, this guy Friedman. Didn't understand much about real astronomy. So he makes a prediction. He says, this is the prediction. I'm making a prediction. I'm going to take the data I can find in 1927, the best redshifts I can find, and some of the distances that are available. He also uses some kind of magnitude stuff for stars, and he comes up with a distance-velocity relationship. And 2 years later, Hubble himself does it. Unfortunately, this guy publishes this extremely important paper in a really obscure journal, and it's forgotten for many years. And he has to remind his old professor, Arthur Eddington, that, hey, I did this a long time ago, but this guy gets all the credit. So this guy gets the credit for coming up with this distance Doppler redshift relationship, even though he wasn't the first to discover it. So life is unfair, even in the sciences. I gave a whole lecture on this to physics students, a whole history talk on this whole thing. Anyway, so again, the more distant an object in the universe is traveling away from us, the faster it's traveling away from us, the farther away it is. That's what this relationship says. And this is essentially the discovery of the expansion of our universe. But this was very early times. So first of all, the original sample size was very small. Those super bright stars that Hubble wanted to use, well, he didn't have super great equipment. He had photographic film. It wasn't super high angular resolution or anything like that. So what he thought were the brightest stars in some of these farther away galaxies were actually clusters of stars. So he was totally wrong. His intrinsic luminosities were way off. So they ended up being much farther away than they realized. They thought they were much closer than they were. And this guy himself, who wasn't really a theorist, he really was an observationalist, he himself didn't even believe in the expansion of the universe, although he gets credit for discovering it. That's another amusing thing about it. Until the day he died, he said, I don't feel comfortable with this. I don't go for it, but anyway. So here's what the law says, that the velocity is related to the distance of the object. The velocity of the object traveling away from me is related to the distance of that object from me, times some constant that we now call Hubble's constant. So he also got one of the most important constants of astronomy named after him. And he wasn't even the first. It's a tragedy. Okay, so V is just going to be what we call the recessional velocity. That's just, you can just think about it as a Doppler shift towards the red. Okay? Hubble's constant, well, in this class we're going to use units of kilometers per second per mega light year. That's the unit of that constant. That's how you get things to work out. And just to remind you, I just want to remind you, we talked about Doppler shift before with the trains, and I played I think a motorcycle thing for you or something. It was quite cheesy. But remember, that's what we're talking about. But we're really talking about redshifts for the most part. In this case, in cosmology, we're talking about redshift. There are some galaxies in the local universe that are traveling towards the Milky Way because we're gravitationally bound. But on very large scales, everything is traveling away from everything else on the very, very largest scales in the universe. Okay, that's just, again, those same plots from that earlier chapter. We talked about blue shifts versus red shifts. There was the equation we used, using the rest wavelength of a particular line, maybe a hydrogen line, and what we observe it as to get the radial velocity. And that was another example just showing how it works. I gave you similar to one of that in the second midterm. Okay, so as I said, this constant is really good over very, very large scales, but individual galaxies will feel gravitational effects from other objects. So again, the local group that the Milky Way is a part of is gravitationally bound. So the objects in that little group will not act in accordance with this law. They will act in accordance with that law with other small groups that are far away from each other. But within the group, they're gravitationally bound, so they don't follow this expansion of the universe law on these very small scales. All right. But, of course, this is astronomy. We're limited by the accuracy with which we can measure that Hubble constant, that relationship between velocity and distance. We can use Cepheids for nearby and white dwarf supernovae to get really big distances. And again, one of the prime reasons for building the Hubble Space Telescope was to nail down these distances. So using the best space telescope we have available to us, we can only get the Hubble constant down to about 20%. But that's pretty good. I mean, that's the accuracy that we have. But it's enough to give us some ideas about the age of our universe and how long it's been expanding. Okay, so this is what it looks like. Again, here's the relationship. And as that constant changes, it will change the recessional velocity. So if it's slightly different, you'll see different objects at different distances. So we basically are fitting the line to the objects for which we have very good distances and very good recessional velocities. And you can see there's some scatter in the line, and that's that 20% uncertainty in the measurement. Okay, so we use physical data to do this. A lot of this data, this is just an example data set. A lot of these nearby are going to be Cepheids, and most of these are going to be white dwarf supernovae in distant galaxies. Okay, so of course, let's figure out how to use this formula. So let's figure out the distance to a galaxy whose redshift I measure as 20,000 kilometers per second. So this particular object has a Doppler redshift of 20,000 kilometers per second. It's traveling away from me at 20,000 kilometers per second. That's not bad. That's not so high. That's fine. I can use that. So I plugged it into Hubble's law. So I have to solve for d in this equation. So d is just going to be equal to whatever the velocity is over the Hubble constant. I plugged that 20,000 kilometers per second, and I told you that Hubble's constant is 22 kilometers per second per mega light year. If I divide these, I get how many light years away from it. In this case, this object is 909 million light years away. Quite far away. But not that far by the scale of the whole universe, but far away. Okay, so I showed this before, how all these things build on top of each other all the way out to the Hubble constant. So we can use this in several ways. As you can see, one is to obtain distances to distant objects. You can use the distance estimates to get an estimate of the age of the universe, and one can also estimate some rough idea of the size of the universe. So let's look at the expansion of the universe itself, and then we'll talk about these distance estimates and size estimates. So again, we know galaxies and universes are moving away from each other on these larger scales. Of course, they all started out much closer together. That's what you can surmise from this, right? If they're all traveling away from each other now, they probably all started out at a singularity. This Belgian guy in the map, he was the first to propose something that he called the primeval atom, he called it. It's a paper he wrote in the journal Nature. And he says, well, if this is what we see, then the universe must have started out as a primeval kind of atom. It started out as this kind of singular device. But nowadays we call that singular moment the Big Bang. That was given to it by an astronomer who didn't like this model of the universe, and he derogatorily referred to it as this silly Big Bang model when he was doing a radio interview on the BBC, and it stuck. So be careful what you call something. If you don't like it and you're famous, it might stick. It might stick. So it's called the Big Bang. All right. So again, the rate appears to be the same everywhere in space. And let's see with this little simulation. So here's the Milky Way galaxy. And that's how the space would expand. Each one will go away from it each time. So let's see if I can. Probably don't need to do the original one. So that's what it would have been in the beginning. It would have been with some other objects in the very early universe, but as the universe expands, they get farther and farther away from each other. That's the idea. Okay. So again, the rate appears to be the same everywhere in space. That's what the theory tells us. And the universe has really no center or edge as far as we can tell. So, I like this balloon analogy that your book uses. I think it's really excellent. So let's try to use that to figure out what we're talking about. So, we pretend the surface of the balloon represents our universe. The people on the surface of this balloon have no idea of what it's like to be off the surface of the balloon. So they just have a two-dimensional world. So the inside or outside has no meaning. So again, just like our universe, no edges, no center, whatever. We can paint the balloon with dots, A, B, C, D, and we're going to inflate it and see how those dots move. So after 3 seconds after the inflation of the balloon, the scientist on dot B sees that dot A has traveled 3 centimeters and has been going at a redshift of 1 centimeter per second. Dot C, 3 centimeters, again, the same redshift. And dot D is farther away from B. It's gone 6 centimeters, and I know that it's been traveling at 2 centimeters per second. Let's see if this should work. So this is kind of what it will look like. Not surprising, it just expands, and I can measure the time of the expansion and how far away they travel over that period of time. So that's the basic premise here. Okay, so every dot from what I just told you from B moves with a velocity of 1 centimeters per second for each 3 centimeters of distance. That's what that tells you, what I just showed you. So if I use Hubble's balloon law for any dot, I can write it as such. So that the velocity for any object is related to that 1 centimeter per second per 3 centimeters times the distance of that dot. So that would be my Hubble law. My Hubble constant would be this 1 centimeter per second over 3 centimeters. Okay? But one nice thing I can do is I can invert the Hubble equation. I can cancel out the centimeters, and I can find out how old this expansion is, how long it's been going on. So if I just cancel out these units and I invert this, I find out that my universe, the lifetime of my little balloon universe, is 3 seconds. And I can do the same thing with the Hubble constant I gave you for our own universe. So all I'm going to do is figure out, to the best of my abilities, I said we know the Hubble constant to about 20%. All I have to do is invert that number and I can figure out how old my universe is. If it's started out with this singularity called the Big Bang. So if I do that, I don't expect you to do this, but I just want to show you that it's possible. So I have to do some unit conversions because part of this equation is in megalight years, part of it's in kilometers per second. So I convert everything over to kilometers, change years to seconds. In the end, I find out that given this Hubble constant that we've measured, that our universe is about 14 billion years old. So when we say that the universe is 14 billion years old, we have some evidence for it. We don't just pull it out of a hat. So that's where that number comes from. It comes from measuring the distances to these distant galaxies, knowing their redshifts, and understanding the relationship between these objects' red Doppler shifts and their distances. And, of course, a solution for the universe of Einstein's general theory of relativity equations. Okay. Well, one thing about this is that this Hubble constant changes as a function of time from the expansion's beginning. So the Hubble constant I measure today will not be the same Hubble constant I would measure from Earth in a billion years. It will change in time. That doesn't surprise you, because as the universe's age, if the universe's age is 1 over the Hubble constant, this Hubble constant better be changing as the universe gets older, right? But regardless of when it's measured, again, it will always tell me what the age of the universe is. If I can measure the Hubble constant at any stage of the universe's expansion, no matter if it's after 1 billion years or if it's after 100 billion years, I can figure out what the age of my universe is. Yes?
This may be a silly question, but how is it a constant so it's changing?
It's a constant today. That's what I mean. So we call it a constant today because, well, for us, the difference between this constant's value today and its value in 1,000 years, no difference. But on time scales of billions of years, it will be different. So it's a constant today. But yes, very good question. Yes.
Is that example of the balloon, like the raisin cake model?
Yes, the balloon is a bit like the raisin cake model, where these points go away from each other as it expands. Okay. Okay, I've already talked about this a little bit. The Hubble constant can be influenced by some other things. But first of all, it can be influenced by the pull of all the galaxies in the universe on each other, right? Because I have gravity here. I have this initial explosion that spews all this matter out, but the matter itself does influence this expansion rate because everything is tied to each other gravitationally, right? There is a gravitational pull between every single object in the universe. And that would tend to slow down the expansion and tend to change the age of our universe. We'll find out that there's another prediction that there may be another force in the universe that is basically pushing apart the very fabric of space over time. We call it dark energy, but we won't have too much time to go into it. And that would do the opposite. It would speed up the expansion of our universe. And that also would change the age of our universe. So whichever of these things is the most important, we have to make sure we put those, to the best of our knowledge, into our solutions and see what they tell us. Okay. One other thing. So the distance to an object, if you can think about it a little bit now that you know a little bit more, the distance to objects, the distance objects, is a little more complicated than I do believe. We really use something called a look-back time. Why is it more complicated? So think about it. Is the distance between us and an object the distance when the light was originally emitted from that object? Or is it the distance after the light has reached us? Because we have this expansion of the universe. So if I have an object that is, 10 to the 6 million light years away, really, really, really far away, and I want to figure out how far away it is, how do I do that? Do I really measure it from when the photon was emitted and then I see how long that takes? It's a little confusing, right? Because you have this expansion to worry about. I'm going to show you how we do it. So we're going to use something called a look-back time. And that's essentially the difference in the age of the universe when the photon arrives from when it was emitted. So a look-back time of 100 million years means the light has traveled 100 million years to reach us. Okay? So of course, this is just related to the expansion of the universe. So again, objects farther away travel faster and faster, and their photons will be shifted to longer and longer wavelengths. Let's see if there's a nice little animation of that. So again, objects that are farther away from us will have longer wavelengths. This is supposed to be an example of this balloon expanding. You can see the wavelength of light has changed from blue, and then it changes to red, basically. So objects that are farther and farther away from us will emit redder and redder information because they're getting more and more Doppler shift. That's another part of the business here. Okay. So this will be another example where I'll show you how the distance between faraway galaxies will change as the light travels. So here we have the location of the Milky Way, location of the galaxy at the time of a supernova, which I'm going to use to figure out how far away this object is, and then the timeline here. So I'm hoping this will help you get a better idea of what's going on. Let's see. So here we are, traveling in time. Boom, the photon travels to Earth 400 million years ago, and then it arrives 400 million years later. So, space-time, here's the Milky Way on a timeline, and you can see the distance on the x-axis, and that time tells us what the distance is. That's how it works. Okay. So, this is what we call a cosmological redshift. So it's this redshift, this Doppler shift we measure, is due to the physical expansion of space. This space itself, this velocity of space itself, that's what causes the Doppler shifts of these objects. Okay? That's what's going on. And this cosmological redshift really does tell us how much space is expanded between the photons leaving these distant galaxies and their arrival at our detector here on Earth, just as I just showed you in that last slide. Okay, so, as I've already said, the universe really does not have an edge. It's not really expanding out in anything we can measure, although there are there's some speculative stuff about that out there, but for the most part, that's how we feel about it. It does have what we call a cosmological horizon. So that's really the limit of our observable universe. Again, it's a time quantity, not a distance quantity. So for our 14 billion year old universe, we basically cannot see beyond that creation date of 14 billion years ago. We don't have any way to measure anything beyond that. We don't have photons of light coming from objects because they're not there. Okay. What's the most redshifted radiation we can measure? That's something that we call the cosmic microwave background. When we go to the next chapter, we'll learn a little bit more about that. But this radiation is from when the universe was 380,000 years old. This is the first time that photons can free stream in the universe. And again, in the next chapter, we'll talk about how that comes about. But at that time, the universe's temperature was around 3,000 degrees Kelvin. Okay? When the universe was 380,000 years ago, its temperature as a whole was around 3,000 degrees Kelvin as it was cooling off from that initial explosion at its origin. That radiation has been traveling for 14 billion years to get here, and it's been cosmologically redshifted from a wavelength of about 700 nanometers all the way out to 2 millimeters. So, as I said, this 1% of the static you see on your analog television are these cosmic microwave background photons that have traveled since the universe was only 380,000 years old. That was one of the predictions of the Big Bang Theory, that we should detect this radiation, and we do. I'll talk more about that in the next chapter. So, another thing I want to talk about is this cosmological principle, with the idea that no matter where you are in the universe will look the same to you. Matter is more or less evenly distributed on the largest scales in the universe, so if I take a really big box of the universe and I average the density in that box over maybe 1 billion light years on each side, that density should be the same no matter where I put that box. Okay? Again, there's no real center or no edges. Think about that balloon. If you're in a 2D world, you don't really have a center or an edge. This principle is not proved, but thus far it's consistent with all the observations that we have made to date. Yes?
When you described the Big Bang, you said it came out of a singularity.
Yeah.
But I'm sort of relating that singularity to a center. Can you sort of describe?
Yes, I know. It's our intuition that wants us to relate it to a center.
Right.
But again, it's not expanding out into anything that we can understand. We live within this object. It's like being on the surface of a balloon. So we can't describe or measure anything off that surface, basically is what it amounts to. So think about it in that sense. I know it's not very satisfying, but that's the best way to think about it, in a way. It's our own short-sightedness that prevents us from seeing more. Okay, let's take another 10-minute break, and then I'll go on to chapter 23.
Okay,